Very much. So today's talk, I'd like to mainly explain what is a holographic calculation of entanglement entropy. So yesterday, I gave a very quick review of AdS CFT, and also I should mention that this very famous and this is a basic principle how to compute physical quantity in AdS CFT. This is called bulk to boundary relation. So this relation is actually very simple. Idea is very simple. That's which claims that some gravity partition function in gravity theory is equivalent to partition function of conformal field theory. As we discussed yesterday, so the gravity lives on this untitled Chapter space in the bulk, and the CFT lives on bound. So we have this equality. This is a basic principle in AdS CFT correspondence, and this is quite useful in our purpose because entanglement entropy is some partition function, basically partition function on some singular manifold. So by using this idea, we can map entanglement entropy in CFT to this gravity picture. And also, we also familiar with the calculation of this correlation functions by using this relation. So we have some external field with some with a dilaton field or a graviton field or gauge field in the bulk AdS. Then at the boundary, it coupled to some operator. Metric coupled to energy stress tensor of CFT and scalar operator coupled to this scalar field reduced at this boundary. And by taking derivative about this external field, we can extract from this relation the correlation function and so on. This is a very familiar calculation of a correlation function in AdS CFT correspondence. And we are going to discuss some modification of AdS CFT, which can be basically casted into three bit rough definition, but there's three different cases. First of all, is starting point is pure AdS. Pure AdS is correspond to CFT at 0 temperature. Pure state. This is a pure state. This is a literal AdS, and we can slightly modify the infrared geometry, which corresponds to large Z direction. And sometimes we can put the horizon. This is AdS black holes. Of course, there are many kinds of AdS black holes. And basically, this corresponds to some finite temperature. The black hole has some temperature, Hawking temperature. So this is dual to some finite temperature conformal field theory. Also, sometimes we have some chemical potential. This corresponds to some charged black holes, which is useful to apply this to condensed matter physics. And finally, so opposite, we can have another modification of infrared region. This is some solitonic modification. There we don't have any horizon like these black holes, and entropy is vanished at the leading order of n large n limit. Black hole is a planar black hole entropy exists, and this is finite temperature. But now temperature is 0, and quantum field theory is mass gap. Mass gap means this degree of freedom is somehow disappear. So this part is extended to infrared region infinitely. That means the theory is conformally invariant. We have massless excitation. But in this case, we have some definite mass scale, and which is finished at this point. And we will discuss these cases as a playground. And so before I go to entanglement entropy, I'd like to mention one motivation from AdS CFT correspondence. So there are many questions about AdS CFT, and there are no precise proof of that. So, but the basic question, one basic question is this kind of question. So we have some conformal field theory, which roughly lives on the boundary. And we have some system A and B. And if we want to just restrict to the information inside A, then what kind of places, what region in AdS should correspond to this information? That is a very important question. And so we somehow expect this region is somehow related to some region in one-dimensional higher AdS spacetime. I'm not sure if we have a unique answer to this question, but at least one of the best answer can be obtained from the entanglement entropy. Because entanglement entropy, so this SA is traced out SB, that roughly measures the information inside this region. So if we compute entanglement entropy, that is doing something very similar to this kind of issues. So we can look at the holographic dual of entanglement entropy. Then we can find what this XA, this region, corresponds to in AdS spacetime. So this is a motivation from the viewpoint, motivation to why we consider entanglement entropy from the viewpoint of AdS CFT correspondence. Okay, so now I'd like to get into the main point of holographic calculation of entanglement entropy. So the calculation itself is very simple and summarized into this formula, which I worked with Shinsei Ryu, who is a condensed matter theorist. And we find this formula, and this works to test it. This formula tested many examples, and always this works well. And this formula tells us that it looks very similar to Bekenstein-Hawking formula, but totally different. Or you can regard this formula as some generalization of black hole entropy formula. So this 4G Newton is just Newton constant, same as black hole formula. But now we take area of some surface, and this gamma A is associated with this subsystem A. So CFT, we take some time slice. We divide space into A and B some way. And the boundary of A is something definite. The boundary of A fixes this division into A and B. And this boundary is extended into the bulk ADS. So this is a codimension to surface. And gamma A there are many such choices. There are many choices which end at this boundary of A. But we pick up minimal area surface. We minimize the area. And fortunately, in geometry like ADS, we have one factor. And that helps us to give us some unique, non-trivial minimal area surface. So gamma A is this codimension to minimal area surface. And we just compute the area, just geometrical calculation using this ADS metric. Then that is the answer to this holographic calculation of entanglement entropy. So this partial boundary of A is the same as boundary of gamma A. And also there is some topological condition which says that this region A is homologous to this gamma A. Homologous to gamma A. And this is actually sometimes it gets very important. And as we know, so this ADS metric given by this Poincare metric. So Z is this radial direction, and this is the Minkowski direction, is X and T is there. And also we have to be careful about the UV cutoff. As I explained yesterday, there is an area row divergence. Leading term of this contribution should be divergent, because we know this area row divergence in quantum field theories. And indeed, in ADS CFT also, we need cutoff, UV cutoff, as we discussed yesterday. So metric divergent at strictly Z equals 0. So we need to put cutoff and restrict to Z, which is G greater than A. A is very small number, which lattice spacing in the dual theory. So the motivation of this is a very intuitive understanding. So one intuitive understanding is that observer is setting A, and so now we are mapping to global coordinate. This is a boundary, and inside this is ADS. This is ADS, and this is a CFT, lives on this boundary. So observer is sitting here, and we divide the boundary into A and B this way. And so in CFT, this calculation is definite. But in bulk gravity case, it is natural to expect some observer see some horizon, like black holes. And the information of B is somehow encoded here. This is related to previous issue of this information region. And so this is sort of horizon. And so then the entropy is estimated by this Bekenstein-Hawking formula. That is a very intuitive understanding this. And in particular case, especially in ADS3 case, this naive identification or naive interpretation is actually correct. And this is exactly Lindorff price. But in higher dimensional case, not completely understood. That I will discuss later. So but first we should show the area row divergence. And this is already clear in the near this boundary region, metric divergent. This Z equals 0, so metric gets divergent. And the main contribution should proportional to this area of this boundary of A, but area of this del A. So this is the area row. And if we compute this coefficient, then 1 over A to the D minus 1 appears. This is divergent coefficient. And indeed, this confirms this area row divergent up to some numerical factor. So basically, always, if we consider some ADS CFT, then always leading term is area divided by this divergent constant. So also, I'd like to mention that my convention is ADS D plus 2. And this is dual to CFT D plus 1. So D is a space dimension of conformal field theory. Then we have this kind of area row divergence. So it is also easy to see that so-called UVIR duality. And so UVIR duality is a basic idea of in ADS CFT. So something UV in the CFT side it gets something small length, which is infrared. And something very large in a probe in a CFT side, it gets into the deep in the inside of ADS. It looks like UV in the gravity side. So, and I'd like to add some comments about this holographic entanglement entropy. Of course, we want to prove this by using the Barak-2 boundary relation, but unfortunately, this has not been done in a precise way. I will give some heuristic derivation, but it's a bit far from complete derivation. So this is a very future problem. Complete proof of a holographic entanglement is still missing. But nevertheless, there has been so many evidences, and so far no counterexamples. We will explain these evidences later. And also, sometimes we want to generalize this formula into some time-dependent background. So implicitly, this formula, we assume that everything is static. So we take we omit time direction. This means we take some time slice, t equals 0, for example, t equals 0 slice. But then we have some minimal area. But if we include time direction, which is typical in, for example, black hole formation or some more general time-dependent background case, we don't have any minimal area surface. If we take into account this time direction, if you have time direction, so if you go the right direction, narrow direction, its area becomes vanishing. So that looks like some minimal area, but that doesn't give correct answer. So in that sense, we should do something different. And so a correct answer turns out to be not minimal, but just we take extrema of this area function. We consider some many surfaces, and we compute areas, and we just take saddle point of this area. This is some variational principle in a Lorentzian geometry. As I worked with Veronica Fubeni and Mukund Rangamani, and this works well in many examples. And finally, in the presence of horizon, sometimes also we have some horizon, like AdS black holes, then minimal surface tend to lap the horizon. And this case, so we assume that subsystem A is very large, then it almost laps the horizon, and that contributes, this formula says that contributes just reduced to standard Bekenstein-Hawking entropy. So this is just horizon area. So the Bekenstein-Hawking entropy is somehow included, and this is sort of generalization of that. Okay, so up to now, I have discussed the general calculation of holographic entanglement entropy. Are there any questions? I'm now getting into some detailed examples. So are there any questions? Yes?
About the last remark.
Yeah.
We have a condition on the size of the subsystem A in order to reproduce the vector.
Yeah. So actually, that is also topic here. Maybe I should explain this first. So this is just AdS black hole. This is a boundary of AdS. I'm looking at some global AdS picture. So this is a boundary of AdS, and inside is AdS. And if we have black hole, there is a horizon here. And the minimal surface, so this subsystem A is getting into this area. This is a minimal surface for this region A. And if A is very large, then this tip is almost reach the black hole horizon, and it tends to wrap this way. We can show this is a minimal area surface. And in that case, this contribution is just reduced to the Bekenstein-Hawking entropy. And indeed, if we compute this contribution, it is proportional to, in AdS3 case, this is BTZ black hole in AdS3, proportional to central charge C, and L is this length, and temperature. This is a really extensive contribution. This is just well-known expression of thermodynamic entropy. And I should also mention that this case, this SA is now different from SB because there are two choices of this trajectory, this minimal surface. So the black hole gives some topological obstruction, and there are two SA and SB. And as I mentioned, so one topological condition, this SA, this region A should be topologically homologous to this gamma A. So we pick up this gamma A for SA, and we pick up this gamma B for SB. And then we get this difference. And this is very natural, because we know that for mixed state, like finite temperature, we know that SA is different from SB. And this difference, roughly speaking, thermodynamic entropy. So is this clear? Yeah.
So is the black hole entropy related to SA minus?
Yeah, exactly. Yeah, more precisely, I mean, we can take SA goes to 0 and B goes to total system, then it almost able just cover black hole. It's precisely agree with black hole entropy. Yeah. So, okay, no more questions? More questions? Okay, so now I'd like to give you a simplest example of this holographic formula, which is the AdS3 CFT2. So now, sorry, this is Poincare coordinate, now not global coordinate, this is Poincare coordinate, more simple coordinate. We have, so this is the boundary of AdS, and this z direction is extended this way. At z equals 0, we have this boundary. And in this case, we can show that the minimal area surface, actually this is a minimal area surface just means geodesic line. It's always codimension 2, so 3 minus 2 is 1, so it's a one-dimensional object whose length is minimum. So that is a geodesic line which connects these two regions, for example. This is separated by 2A. And we can show that this geodesic line is just half of the circle, round circle, half of the circle, this L and L. This is a good exercise, and maybe you can try it later. But this is very nice result is that this is just half circle, and the half circle is just given by this familiar formula, and the radius is small l. And the induced metric on this half circle from this metric is given by this. And we just integrate about L to the z into L. L is cut off. Sorry, A is cut off. A is cut off. A is cut off here. And to L is the maximal value of z. So we integrate this way. And we put 2 because we have two copy of that. And this integral, as is clear from this ratio dz over z, this is logarithmically divergent if we set a equals 0. A is cut off, and it is logarithmically divergent as expected. So from that, we can take the ratio of this geodesic length divided by 4g Newton. This is a holographic formula. We get this ratio. And then we use a famous relation in AdS3, and this is a relation between central charge C of two-dimensional conformal field theory and the radius of AdS space-time, Brownian relation. And we plug this in, we can just replace the C, then C over 3 is reproduced. This exactly precisely agree with what we explained yesterday. It's two-dimensional conformal field theory result. C over 3 is typical coefficient and logarithmic about length scale, so this appears. And also this breaks some area logarithmic. So also we can do the same analysis for finite temperature case. Already I quickly explained it. But so finite temperature case, the simplest example is again AdS3 case, which is a BTZ black hole metric given by this. And this case is computation a little bit complicated, but still you can do it analytically. And this is also a good exercise actually to derive this length of geodesic line. And in the high temperature limit, this is high temperature limit. Beta is the inverse temperature, and L is the length of subsystem. We take length of subsystem, it's very large. Then this high temperature limit. Then we can have this BTZ black hole is dominant contribution, and we can just compute geodesic line in this background, and finally we get entropy, holographic entropy. And this precisely again agree with two-dimensional conformal field theory result. And this already I explained, so I skip. So this formula computes this region, this length. And you can see that if we take high temperature limit, beta goes to 0, then this is exponentially divergent. So from there, you have some exponential, and we take log, so we have linear term about L. So linear about L means extensive, and this is precisely this contribution where minimal surface wraps this horizon, this contribution. And we can naturally extend this analysis to higher dimension. And also, I'd like to mention another point of this disconnected subsystem. So far, and also rest of my talk, I'm assuming that the subsystem itself is just connected manifold, connected submanifold. But sometimes also we can consider some disconnected subsystems, like subsystem A consists of this interval plus this interval. Then we notice that there is a phase transition. So this is worked out Matt Hedrick, and he showed that this phase transition is consistent with conformal field theory calculation done by Carbret-Carty-Tony, and consistent with this calculation if we take Lagian limit. So of course this is semi-classical gravity picture, so we need to take Lagian limit. And so this phase transition means that so we have this length, so we have minimal surface of this way or this way, so we can connect this region. So this is one choice, and another choice. And we always take sum of this length, and we have to minimize everything. So When this is smaller compared with this one, then this is dominant. But if we assume A1 and A2 is separated largely, then this configuration gets dominant because this has a smaller length. So there is some sharp phase transition, and this, of course, should be come from this large n limit. And finite n probably this is smoothed out. And so this is some simple examples. And before I go on to other examples, I'd like to explain some heuristic derivation of holographic entanglement. But I have to say this is far from the proof. But this helps us to understand how we get that formula. So this argument is mainly based on the paper by Full-Side. So let us try to derive this holographic entanglement from the bulk to boundary relation of AdS CFT. And we know that in CFT side, this is a partition function on this manifold, n-seated Riemann surface. Two-dimensional case, n-seated Riemann surface, but higher dimensional case, some n-seat geometry. And this is partition function is equal to this trace A to the rho A to the nth. This is I explained yesterday by using path integral formalism. And for this cut, so we can say there is a deficit angle, negative deficit angle, 2 pi 1 minus n. So this is rather singular geometry, as if we keep this pictures as it is. And the assumption is that there is this singularity, deficit angle, and this AdS dual of this is we should extend into radial direction, z direction. And the idea is that just assume that AdS dual is just given by extending this deficit angle into this bulk. If we admit this assumption, this is assuming that this is a true answer, then we can compute contribution to the gravity partition function. So we know that if we have deficit angle, we have this kind of divergence, delta functionally divergent piece of Ricci scale. And always n minus 1. N equal 1 is regular geometry, so n minus 1 is coefficient of this delta function. And if we assume this is localized, this delta deficit angle surface is like this gamma A, then it's localized on this delta function localized on this gamma A. And we evaluate. Of course, we have a cosmological constant term, but that doesn't affect this argument. So only this Einstein-Hilbert term is important, and it leads to n minus 1 times this delta function, so it's localized, and 4 pi is cancels this 4 pi here, and area of 4g Newton appears. And then we take derivative about n. This is a replica method, and this is the entanglement entropy. And precisely we get this area divided by 4g Newton. And we impose some variational principle that this gravity partition function should be stationary. Then this is stationary. This means that gamma A is a minimal area surface. So this is a intuitive. Yes?
Can you say again why the curvature is delta function on the whole gamma A? I mean, there is a delta function on the...
Yeah. That is the assumption. Yeah, so sorry. Yeah, this is the assumption here. But as you say, this is not guaranteed. You're right. Yeah, so this is a very subtle point. I'll come back. But if we admit this assumption, we get this very simple result. But however, this argument is not completely correct, because the assumption, as Radesh pointed out, can easily fail. And indeed, this assumption is not correct. If this assumption is true, then we can, for any n, we get this result. But this is turned out to be not true. If we literally compute some linear entropy, this for finite n, linear entropy for CFT, we get different result. So that's case. That means this is not completely correct. So this trace of n is not correct. But holographic formula, to derive holographic formula, we don't need the value n equal 2 and 3. So if we assume this assumption is correct in this limit, n goes to 1 limit, then everything is okay. So this is the situation. But of course, there are no rigorous proof of that. But if we admit that, then that works. At least this gives an approximation of the real geometry. Then this is sort of variational principle approximation, which people do in quantum mechanics. But to exactly derive, then we have to show this kind of very subtle issue. So instead, people try to examine some specific examples so that we can compute in both sides exactly, rather than just show these generic examples. For example, this recent work with Cassini and Frelta and Myers, they particularly focus on the case where boundary of A is just real, most symmetric round sphere. Then we can do the calculation explicitly, and this gives a direct proof of holographic entanglement theorem in this particular case. But if we have some complicated geometry, still it's not completely proved. Okay, so any questions?
So this was in the limit where you have Einstein gravity.
Yeah, that's right.
Is there any proposal for going away?
Yeah, I'll come back to the higher derivative correction. Yes, I'll explain just next to next transparency. So, yeah, so also I'd like to mention the so yesterday I mentioned this very important inequality called strong subadditivity. This kind of summarized into two inequalities. But actually in holography, this can be easily shown, just a few seconds. If you look at this picture, so you understand the idea. And so we just reduce everything into 2 dimensions. We can do it in a higher dimension, but essence is contained in the picture. So this is the AdS boundary. This is the AdS bulk. This is Z direction, and this is the AdS boundary. And A, B, C is like this. And we just, for SA plus B, we pick up A plus B, and we pick up its corresponding minimal area surface. Minimal area, the B plus C is like this blue curve. And we can just regard this way. This is a green line, and this is brown line. So still, total sum is the same. But actually, this green curve is surface for A plus B plus C, and there should real minimal surface. This is totally different from that. And also similar is true for this curve. And this way, this inequality is already clear. And this inequality appears because we have extra dimension, which is the essence of this holographic idea of holography. And the other inequality also can be shown in a more simple way. But now we'd like to come back to the issue that when we can have this inequality. So of course we start with some minimal area surface, but this is always true. This inequality is always true if we assume entanglement entropy is minimum of some function, any function of some gamma A. So this allows us to modify this kind of analysis, and this is actually related to this largest question that we can take into account higher derivative corrections. So if we have higher derivative terms, then this function is corrected. Before that, I also would like to mention a recent application of this kind of idea. This is done by Hayden with quantum information people, and this is Matt Hedrick and Alex Maloney. And they show very interesting inequality, which is called monogamy. This inequality is rather very important in quantum information theory. But I think, to be honest, it's quite difficult to understand, intuitively. But this summarized into these inequalities. So this is, if we forget about this AC, so now I slightly changes notice. So this just AB means A plus B, B plus C, and A plus C. And this is mutual information between A and B and A and C. If we forget about this, is just equivalent to strong subadditivity. That means this inequality is more powerful than strong subadditivity and independent from strong subadditivity. And if we rewrite everything in terms of entanglement entropy, we have 7 terms. But this 7 terms actually appeared in the calculation of topological entanglement entropy, precisely the same. This says that topological entanglement entropy is non-positive. But this proof of this formula is very similar to the previous proof of strong subadditivity. It's already clear from this picture. But of course, we can work out also other cases, and so we have to be very careful to show, but essence is this kind of inequalities. And this roughly says that if A and B is really strongly entangled, C is somehow isolated. C cannot be strongly entangled with other guys. This is this intuitive understanding, this monogamy relation. And this is not always true. If we take quantum field theory, this is not always true. For example, if we take free field theory, free scalar field, this is violated. But AdS CFT, and assuming this generalization, says that this is always true. And so higher derivative correction corrects some large n, but still, weak coupling as a coupling expansion, strong coupling expansion. So holographic entanglement entropy argues that this is true, this kind of inequality is true for large N gauge theory, for any coupling constant, if you have a holographic dual, of course. And also, particular case of this inequality leads to so-called, it is a bit technical, Kadoni-Linden-Winter inequality. This is a bit famous inequality in this context because this is independent from strong subadditivity, more stronger the version of that inequality. So this we can also show this inequality. And more recent also, this kind of inequality also holds in time-dependent background in explicit examples as confirmed. These people?
You said this is true for any.
Sorry.
This is true for a large N.
Yeah, that is a prediction from ADS CFT.
But at lambda equal to 0, you said it's not true. I mean, for free theories.
Yeah, but I'm talking large N limit. So we need something like symmetric overhold or something like that, I think.
Or the Gauss law constraint.
Yeah. Of course, I mean, for weakly coupled, but I'm forgetting about non-perturbative corrections. So perturbative expansion from strong coupling limit. That should correspond to this kind of modification. If we take into account non-perturbative correction, I'm not completely sure about it. So, yeah, and I would also come back to the correction to this holographic entanglement entropy. So consider the stringy correction. So there are two corrections in ADS-CFT. One is stringy corrections. Another one is loop corrections. G-string. The stringy correction is related to alpha prime expansion. And the loop correction, quantum gravity correction related to G-string. And forget about this G-string correction, quantum gravity corrections. We still keep, this is dual to large N limit. Still we keep large N limit. But we can perturbatively take into account the stringy corrections. So this is a rather simple setup, which we can think of. But unfortunately, there are no complete answer, even though many people worked on that. But the nice result is obtained by Hun, Myers, Smolkin, and also Dvorak, Kudarsky, and Parnachev. And they show that in particular class of higher derivative gravity called Lovelock gravity, and we can construct holographic entanglement entropy formula. But basically, very similar to Waldo formula. But this naive Waldo formula doesn't work for other more general higher derivative gravities. But for this case, roughly speaking, Waldo formula, it works. So if we take particular example of Gauss-Bonnet gravity, which has Einstein-Hilbert term and also cosmological constant and Gauss-Bonnet term, this R-square term, Gauss-Bonnet coupling, then the result looks like this. So we have this leading area of time, but also we have curvature corrections, which proportion to this Gauss-Bonnet coupling, lambda. So we can use this formula to calculate this entanglement entropy in slightly off from strong coupling limit. But unfortunately, there are no complete answer to more general cases. Yes? Yeah. Good. The difference between this and Waldo formula, this is more general. And the surface don't have vanishing extrinsic curvature. If you have a horizon, it has a very nice property that it has a vanishing extrinsic curvature. But here it's more general, so we have some ambiguity to fix. That is the main problem. Everything is very technical, I should say. But so far we don't have any nice formula for general case. But the particular case we have this. For example, there is so these are actually induced metric on this gamma A. We can also equally add some X-ray curvature, but that is not allowed to do that to reproduce sensible result. Okay, so now I'm come to the higher dimensional case, explicit calculation. I don't take into account higher derivative correction now. So the particular case we look at is these two cases. There we can have some analytical result. This is a straight strip or belt type subsystem with reduced L. We can just replace this A and B because SA equals SB for 0 temperature case. This reduced L, small l, and this infinitely long length direction is a large L. And we have also talked about the circular disk. And in both cases, we can find analytically the holographic dual surface, gamma A, entangling surface, this way. This is just half of the sphere, precisely half of the sphere. This is slightly complicated, but we will have some, you can get some analytical expression of that. So the first one, this case, it has I have a translational invariance in this direction. And result also looks very simple. We have two terms. First term should be there because this is area row divergence. And second term is some finite constant, which is very important because this doesn't depend on the cutoff divergence. And for example, if we set equal 1, they cancel out and taking this logarithmic ratio. And this just agree with two-dimensional CFT. Already we derive this from the principle. But in general, we have two terms. So in this sense, this looks like some Casimir energy type contribution. And we can focus on particular case of AdS5 CFT4, which we know that its holographic dual is n equal 4 supermu theory. So we can compare. Basically, we can compare between two sides. But unfortunately, CFT side is quite difficult to compute if we have interactions. So we we do some free CFT calculation. Still, some result should be some numerical. And we can get this functional form for free CFT. And gravity side, we get this result. This we can express the analytical expansion for that. But they are slightly different. But of course, this is OK because this is just free CFT, and AdS side is strongly coupled limit. There should be some nice interpreting functions. But this functional form precisely agree with each other. This is similar to this for surge factor in thermodynamic length. And so the next case, this case, it has some curvature. So according to this curvature, there are lots of terms appears. So we can fix each terms analytically in holographic calculation, but as listed here. So this entanglement entropy computed holographically has some 1 over g Newton factor related dependence. And leading divergence, again, of course, area row divergence, like this. And it ends up with constant when d is even. This means that d plus 1 is total dimension, so CFT lives on odd dimension. And CFT lives on even dimension, we have some logarithmic divergent term. And we have a constant, but this is not universal. It depends on the definition of A, so we just forget about it. We didn't write it. But in odd dimensional case, we have a nice constant. So this is some candidate of some analog of central charge in odd dimensional conformal field theory, and sort of we expect some sort of theorem. And about this, there are several developments. And first of all, for holographic calculation, we can show that this is monotonically decreasing under RG flow by works by Myers and Shinha. And also from different viewpoint, that means totally different viewpoint from this is conformal field theory viewpoint, then this is connected to F theorem. As explained yesterday, this entanglement entropy for special case of this round sphere subsystem, then that is equivalent to the partition function on sphere, just partition function of spheres, which is just F, something people call F. And this should decrease under the RG flow and some perturbative proof and so on. They are also holographically you can show that. So that leads to this kind of development. And also this, on the other hand, this logarithmic term in even dimensional conformal field theory. So 2D CFT, this is something we know. This is just C, central charge C into the CFT. And for dimensional case, we are assuming this is a round sphere. So as I explained yesterday, this precisely agree with central charge called A for -4 times A. And we can confirm this by comparing between two sides. So this is another general setups. And if we slightly deform this circle to more distorted circle, still this expansion is true with different coefficient, but this expansion is true. But if you have some singular configuration, so like this subsystem A and subsystem B, it has some cusp. If this is smooth, there are no this result is false. But if you have some cusp-like singularity, then there are additional term, logarithmic divergent piece in 2 plus 1. I'm assuming 2 plus, particular focus on 2 plus 1. Dimensional conformal field theory has some logarithmic divergence part. But always, if we have a logarithmic term, the coefficient is something universal, so something we are interested to look at. So this coefficient is parameterized by this angle omega. So this function of omega, so f omega we have. And the SA equal to SB at 0 temperature says that this kind satisfies this equality, reflection relation, and strong subadditivity is lead to the second derivative of this function is positive, greater than 0, well, 0. So this is strong. So strong subadditivity is lead to some concave thing, but we have some minus sign somehow, so we get this it's positive. And this is actually, to show this is good exercise again, so strong subadditivity. And this is just formal result from CFT side. And these people Cassini and Huerta compute this coefficient f omega for free field theories, like free scalar field and free fermion theories. And also we can do the AdS CFT calculations. The result looks like this. So we need to do the equation. This is integral equation. So omega in terms of some integral whose parameterization is beta, and some f omega is also parameterized beta. We need to eliminate beta to relate these two functions. But anyway, so we can plot this way. This function f omega looks like this. Indeed, the second derivative is positive. It's this convex function. Second derivative is positive. And also, interestingly, so we can compare this result with free field calculation. This is done in this picture. So this is free scalar and fermion computed by this paper. And this, you can see that this number, it's very small, 1.005 or 1.01. Even, of course, this holographic calculation is expected to be true for strongly coupled limit. And the deviation, this angle of this omega, its deviation looks very small, less than 1% or 2%. This is slightly surprising result, which more detailed understanding is not known. But anyway, encouraging sign of this holographic formula. Again, this proof. So we don't have this complete proof, but there are many evidences, as I mentioned, and some of them already we have seen, but some of them not. And I just listed these evidences. So we already see area law, and also AdS3, CFT2, and strong subadditivity, and also this consistency with this disconnected subsystems, and also agreement of this coefficient of log terms, and so on. There are many other evidences for this. Okay, so yeah, so far we discussed mainly holographic entanglement entropy for pure AdS and also AdS black holes. Now I'd like to come back to the other example, which is mass gapped case. Of course, you can find many different examples of mass gapped gravity duals, but I just pick up particular one, which is called Ads Soliton. But you can generalize this analysis to other backgrounds. There are several literature of that. And so here we'd like to study, so in mass gap case, we have some gauge symmetry. So mass gap appears if we have some confined gauge theory. So we have some confinement. But if we heat it up, we have deconfined. So there are phase transition between confinement and deconfinement phase transition. And such phase transition is clearly seen in the gravity dual called Ads Soliton. I will explain. This is, roughly speaking, some infrared region is capped off here. And this is the boundary of this AdS region. And we take this kind of strip type subsystem and with this L and change this L and try to probe this confinement, deconfinement phase transition. So what is the Ads Soliton? So Ads Soliton is very simple, just double weak rotation of the Ads black hole solution. This is a well-known Ads black hole solution, black brane solution. Fr is a function. So this is embedded in the AdS5. And this Fr is this function. This goes to 0 at the horizon. But now we change this t with this other x direction. We extend t and x1, putting I, and we get this background. Now this factor Fr is mapped to these spatial directions. This circle, thermal circle, shrinks at R0. So originally this is the horizon, but now it's just, this circle is just really spatial circle. At this point, space-time is really terminated, as this described in the picture. This is dual, known to be dual to pure IMU theory. So this is compactified. So AdS5 is dual to CFT4, 4-dimensional. But we compactify one dimension. So this is effectively 3-dimensional gauge theory. And this compactification breaks supersymmetry. So fermion has a mass gap. And also boson, scalar field also quantum mechanical mass gap. And reduced to just pure IMU theory, which is really confining. So 2 plus 1, approximately this reduced to 2 plus 1 dimensional pure SUN gauge theory. And in the holographic calculation, you can show that indeed there is a phase transition if we change this value of L. So we have a final result looks like this. So this is a plotted entanglement entropy, holographically calculated entanglement entropy, and we subtract some common divergent piece. And this is the length L. This is L. So when L is very small, it looks like this. It looks like this red line, red curve is here, going here, and this is a rather continuous non-trivial function, and which is just almost approximated by conformal field theory.
What's L again? Is the radius of the system?
Sorry. L is, so size of the subsystem.
Oh, subsystem.
Yeah, L is size of subsystem. So basically, this is a scale which we probe this geometry. So when L is very small, we are looking at short distance in CFT side. Sorry.
The temperature is 0?
Yeah, temperature is 0. Yeah, temperature is 0. But still, we can additional another temperature, which is 1 over L, roughly speaking. And L equals 0, then we have some very high energy situation. This is asymptotically free, so everything is conformal. So it's non-trivial result here. But if we get into L is very small, very large, which go to infrared region, then there is a phase transition at this point. We pick up smaller one. This goes to this just very simple constant contribution. So there are no dynamics is expected for low energy. This is consistent because we have mass gap due to confinement. So this point, this transition point is sort of confinement, deconfinement phase transition point. We have this connected surface for this green infrared geometry. This is trivial, but for this, when L is small, it is like UV geometry. There is a non-trivial minimal surface is surrounded. But if we increase L, this should go to this disconnected branch, and then we have trivial result, which doesn't depend on the length between this size of subsystems. So this is a confinement, deconfinement transition if we look at this entanglement entropy. But we keep temperature is always 0. So in summary, we get this kind of result. So L goes to 0, which is asymptotically free region, UV region. You have non-trivial dependence, power law dependence, which like CFT. And for large L, we go to the just trivial contribution, constant trivial. So, but this kind of sharp transition, of course, should be true only in large N limit. And it is interesting to look at finite N. And recently, there are several lattice calculations done by these people. And so I just pick up their final result. And so, so actually, transition is not that so sharp. So this is a length L. And they plot actually not SA. They're not plotting this, but they plot derivative of SA by L. Del SA by del L. They plot it. So that means here it's positive. It's very large. It's go very large, and some scaling in CFT kind of scaling appears. At this point, it somehow scaling stops and becomes trivial. So very smoothly, but there is some sort of phase transition point. Looks like crossover, but there are some phase transition point appears. And this is SU2. Okay, this is lots of, I think, error, but somehow you can see some transition. But anyway, the problem of this lattice calculation is that, of course, we cannot take n goes to 1 limit. We have to do replica method. We call rho a to the n equal 2 or 3, and then we interpret it. So there are lots of, errors. But I hope this is developed soon somehow. So this is a case of this AdS Soliton, but also we can slightly modify the situation and into some so-called twisted AdS Soliton. And twisted AdS Soliton is some sort of gauge theory on twisted circle. So now Z is some complex coordinate. Previously, Z is not transformed. Z is trivial. And X1 is some compactifier. X1 is a compactifier direction. But also at the same time, you can rotate this transverse direction, this angle of z. You can rotate in R2 direction. Then you have more general twisted geometry. And this previously we worked out this Sharp-Schwarz compactification dual to AdS Soliton, which is corresponds this is 0. This parameter is 0, but pure AdS this is 1. This is of course exponential 2 pi is 1, but for this case, but this is, we are including fermion, so 2 pi rotation. If we have 2 pi rotation, then fermion changes the sign. So this case non-supersymmetric, and this is supersymmetric. In this way, the twisted boundary condition means that we have interpolating between Sharp-Schwarz circle case and this pure AdS case, supersymmetric case. So this means that we can have some small violation of supersymmetry. And its dual geometry is just given by double weak rotation of, I don't get into detail, but some double weak rotation of R-charged black hole, rotating black hole in S5 directions. So the result looks like this. So this is a twist parameter. Here, the supersymmetry is mostly broken, completely broken. And here, this is a supersymmetric point, just purely AdS5 cross S5. This is the AdS Soliton. So, and we plotted this free amused calculation. So interestingly, as we approach towards this supersymmetric point, this gradient computed in free amused theory precisely agree with this calculation of this AdS calculation. Of course, the AdS side is strongly coupled, so this agreement should be related to some sort of non-renormalization theorem, which is not trivial. But somehow, yeah?
Is it some kind of index?
No. This is just full partition function.
Yeah, but at the, I see. So at the supersymmetric point?
Yeah, this break, I think this breaks, yeah, supersymmetry. But maybe I have to be careful. Yeah, that's maybe good, very interesting suggestion. If this is supersymmetrically protected, then you can understand. Yeah, so, okay, so, how shall we do? So, yeah, maybe it's good to stop here, maybe. So, can I ask questions?
Well, let's first thank Takashi and then we take questions. Can you use your microphone? Oh, you don't? Okay.
Sorry, you mentioned about the level of gravities where there is a formula, and did you say that it's not the same as the wall formula? The coefficients are different?
Sorry, coefficients are different, not different, exactly same. But this case, maybe I'll come back to this case. This is a this case, the coefficient is the same as the Barlow formula, but the interpretation of this, for example, R is non-trivial. So, whether we take into account the extrinsic curvature or not.
But you're saying R is the intrinsic curvature?
No, we don't include. We cannot include extrinsic curvature. That is the result. If we want to use this formula to adjust what is known, then this R is just curvature of induced metric of this gamma A.
That's what it is in the Wald case also.
The Wald case is that kind of difference is a bit ambiguous because extrinsic curvature is vanishing. So you can add it still, but this is
in the Wald case, I thought, at least for the Gauss blocking, you have the induced metric on the horizon on some time slice of the horizon, and then you look at the integral of the curvature associated.
Right. Yeah, but the particular case that, so if we assume this is applied to black hole, that reduces. But it is difficult to go different way, opposite way. So we know Wald formula, but it's quite difficult to guess what happens for this term precisely. Should we include extrinsic curvature or not? That is a very subtle point.
I mean, the usual Wald formula assumes some AdS2 in the horizon geometry, right? Which there is no analog here. Okay, it doesn't assume extremality. But see, it takes as an input the geometry near the horizon, where here, this is a...
Yeah, but this bifurcate horizon is very strong condition. Yeah, so
Here you neglect the back reaction.
Sorry.
There is no back reaction from this minimal surface onto the bulk geometry, right?
back reaction.
There is no, you don't take that into
Yeah,
account.
we didn't get some.
And I had one more question about you had in different dimensions this expansion in powers of the UV cutoff, L over A to various powers.
Yeah.
So isn't this scheme dependent?
I was about to ask the same
so-
question.
But you can remove it. Algebraically, you can remove if you know this dependence somehow. This in conformal field theory only this L and A appears. So
It looks like you're assuming some specific normalization scheme, right?
no,
Otherwise,
I
the
mean,
dependence on the cutoff will...
But if we compute SA for if we assume this, we don't know what the A is, but we can compute SA for any L. So then we can, from that information, we can reproduce this term. We can just subtract by taking some linear combination of, for example, SA.
Somehow you match the leading term, which goes like the area, and the
Area
finite
is not-
term.
Area
But
is-
there are some contributions in between which should be scheme
Right.
dependent. Right?
Yeah. So this part is ambiguous. For example, this.
But it's unclear to me why the finite term should be scheme independent.
But it's independent of this cutoff. That is that. So we can in principle compute it.
I guess he's saying that it's independent of L. I mean, in the even dimensional case, you take some d minus 1 derivatives with respect to L. And
Yeah, right. Yeah, something like this.
and then whatever is
Yeah.
is the thing.
Right. Yeah, that's what.
Any other questions beyond those of Rajesh? Yes, please.
In AdS CFT, you compute Wilson loops too by minimal surfaces. So is there a link between Wilson loop
That's
and
a very interesting point, but the dimension is different. If we consider AdS5 CFT4, Wilson loop is always fundamental string. It is, if forget about the M0, it is like just 1 plus 1 dimensional surface, right? But the AdS CFT is always codimension 2, it's a 3-dimensional surface. So if dimension is different, then result is rather different. Sometimes we have this log term, but if we change the dimension by 1, then we don't get log term.
Okay, but in some dimension it coincides. In
In particular case, that's true, I think. But if we take into account higher derivative correction and so on, maybe different, should be different. But at this leading order, large and strong complex. So if we look at very particular.
Ali?
This monogamy inequality, what is the physical content of it in the gauge theory style? What does it say, basically?
That is very difficult thing I should explain. Yeah, but basically this means that if A and B is strongly entangled, C cannot be entangled with other guys. That kind of property appears. Yeah, that is intuitive.
Any other question? Okay, let's thank Takashi for the next lecture.
Thank you very much.